Alright, welcome back. In this video I just want to go over how to find the characteristic polynomial of a matrix. And in this case the example I'm going to be using is a 3 by 3 matrix. So the way that we write the characteristic polynomial, we denote it like a function of lambda, and it's really just equal to the determinant of this matrix that we call A minus lambda I. Now, if you remember from last videos, this is a matrix A minus lambda I, and this is just the result of performing some matrix operations to this original matrix. So if we have the identity matrix like this, and then we just multiply a scalar that we're going to call lambda to it, we just get this matrix right here. So if we think then, what is the matrix that is A minus lambda I? Well, that is really just matrix addition or subtraction. And we're left with this matrix here, where basically we're just subtracting lambda from each of the elements that's on the main diagonal. Now, if we want to take the determinant of this matrix, you can do that using cofactor expansion, or you can do it using the shorthand method that I like to use. So we set up the matrix like this, where we've just changed the lines here to the determinant lines, and we've taken the first and second column and placed them to the right-hand side. So now, instead of going through and doing the full process of cofactor expansion, what we do is we take these diagonals that are going from the top left to the bottom right, and we take the product of each element along those lines, and then we sum it up for each of the lines. Then what we do is we go the other way, from top right down to bottom left, and we subtract the products of each of these. And that's just going to be a bit of a faster way for us to find the determinant of this matrix that is A minus lambda I. So if we write that out, first of all, for the blue lines, we get this. And then when we go through and do the green lines, we get the next three terms. And when you have matrices that have zeros in them, then typically a lot of these things are going to cancel out. So we have a 0 in this term. It goes to 0. That looks like a 6. This one goes to 0, this one has got a 0, and this one also goes to 0, which makes our life a lot easier. So if we take this one step further and simplify the remaining terms, which is just one term here and one term here, we get this, and then we can distribute this last set of brackets. And again, a lot of stuff here cancels out. We have negative 120 lambda and positive 120 lambda, and then negative 240 and positive 240. And I guess I opened the bracket there, so I probably should have closed it here, but either way, it actually doesn't really matter. We can actually just get rid of those brackets for now. So when we do the final simplification here, we get negative lambda cubed plus 36 lambda squared minus 68 lambda. And this is the characteristic polynomial of A. So if that's all your professor is looking for, then you can put a box around it and stop here. But often the reason we're even finding the characteristic polynomial of A is because we're after the eigenvalues and eigenvectors of a matrix. So basically, if we just set the characteristic polynomial of A equal to 0, then we call it the characteristic equation. And if we can find the roots of this equation, then those will be the eigenvalues of the matrix. So if we just simplify it in a few steps, we're going to find that the roots are 2, 34, and 0, and these are the eigenvalues of the matrix. And so if you were also looking for the eigenvectors, then we could use these eigenvalues to calculate those. But this video was just really about finding the characteristic polynomial of matrix A, and so if you get to this step here where we have the blue box around it, then you will have found the answer to the problem of just finding the characteristic polynomial of the given matrix.